I'll start the recording. Okay, so today we will cover factorial ANOVA, right, and repeated measures ANOVA. So it's quite a lot. I hope I will make it and still leave you some time to talk to your other group members about the assignments. I will try my best. So many things are repetition, so hopefully we can go over it a little faster than as if it would be completely new. All right. So if we observe several factors at the same time, so that means we're interested in the influence of more than one variable on some outcome. So let's say, so we were talking yesterday about this Viagra example, right? And how the different doses affect the libido. Let's say, so we were interested in some other additional factors such as age, right? So whether there's whether age has an effect as well, and maybe there's an interaction between age and dose, right? So that would be a factorial ANOVA. And so the simplest case of the factorial ANOVA, where you have several factors, so several independent variables, would be a two-way ANOVA. So two-way means we have two factors, right? So we are examining the influence of multiple categorical independent variables on one continuous dependent variable. So just for your information, we're not talking about that, but there's also the multivariate analysis of variance methods, so called MANOVA, right? So it's an M. And those are basically the methods that have not only multiple independent variables, but also multiple dependent variables, so multiple continuous dependent variables. But that would be a like topic for a separate lecture. And so the research design in which the levels of two or more factors are combined is called a factorial design, right? So once again, so I mentioned that before, the ANOVAs are statistical models and associated procedures. They are not research designs, right? So they don't have an ANOVA design. ANOVA statistical method. That's the analysis part. So it's not the design part. Design is a factorial design. Okay, so as I said, so the simplest case is a two-way ANOVA, where we have two independent variables, right? It's called two-way. That means if we had three independent variables, we would call it a three-way ANOVA. If we had four-way ANOVA, etc. And we also identify our ANOVA model by the levels of each factor. So it means if we have a two-way ANOVA with two independent variables, two factors, and let's assume so the first factor has 3 levels and the second factor has 2 levels, then we would call it a 3x2 ANOVA. Yeah, so a two-way ANOVA, 3x2 ANOVA. So the first factor 3 levels, second factor 2 levels. If we had 3 factors, so 3 independent variables with 2 levels each, then we would have a 3-way ANOVA, and also called a 2x2x2 ANOVA, right? So if the 3 factors at 3 levels would be a 3x3x3 ANOVA. So that's some common notations that you might be familiar with already, but I wanted to mention it. And so it's important to keep in mind so that for the factorial ANOVA, we have different participants, or more generally subjects, right? So observation units, doesn't have to be humans. We have different observation units in all conditions, so in all different conditions. So that means in all groups and all cells of our design. So here is an example from also social sciences. So where we have so decision-making skills as a dependent variable, and there are 2 independent variables. So the first one is so the branch of the armed services, so whether it's an army, navy, or marines. And the second factor would be ranks, right? So we have 2 levels only for ranks. It's enlisted or officer. And then, so that would be your first factor with 3 levels, second factor with 2 levels. And so for each individual cell of this design here, for each conditions, for each factor, also called factor level combination, we have a different sample, right? In this case would be 5 subjects in each cell here. So what would be a balanced design, right? So we can also have unbalanced design where the numbers are different, and our total sample size would be 30. Right, so there are other examples if you were interested in the influence of word number. Well, let's say we have 3 levels, so 2 words, 4 words, or 6 words, and word length with possibly 2 levels, so 3 to 4 letters or 10 to 15 letters on reaction times in a short-term recognition task. So then it would be a 3x2 ANOVA, right? So 2-way ANOVA. Or we're interested in examining difference in income, so that would be our dependent variable as a function of region. So that would be the first factor, has 4 levels, so north, south, east, and west. And religion would be our second factor with 3 levels, Catholic, Protestant, or other. And then sex might be a third factor, a third independent variable, could also have like 3 levels. Then that would be a 3-way ANOVA, so a 4x3x3 ANOVA. Right? Okay, yeah, so and how many groups do we have in each example? I mean, yeah, here we already said it's a 3x2 ANOVA, so that would be 6 groups, and here we have a 4x3, so that's 12x3, 36, right? You can see this design is incredibly complex, so it's a huge sample. Right? So I just want to introduce a little bit new terminology and notation so that you will encounter frequently. It varies though. So there's a lot of preferences and there are many conventions, and so it's not always the same notation used. But so it's very common, for example, for the 2-way ANOVA, that the levels of the first factor, factor A, are symbolized as P, and the levels of the second factor B symbolized as Q, right? So that is relatively common. So these notations, and I mentioned that before, that's a combination of 1 level from each factor is called a cell, right? So if for a 3x2 design, we have 6 cells total. Okay, and so the number of cells obviously is the same, it's identical to the number of groups. And that means the total number of participants can be calculated as n times p times q. So n is the number of participants in each, or subjects in each cell of your, or in each group of your experiment, of your design. And that of course is only true if you have a balanced design, which I mean, so normally you wouldn't start out with an unbalanced, so you wouldn't plan that, right? So that is usually something that happens and then you're annoyed. It's nothing that you plan to do when you're designing your study. Okay, so especially since the behavioral sciences, there are 3 common reasons why we would want to include a second factor in our study design. So we do not only want to make it more difficult for us or like test larger samples, right? So that's more expensive and also more time consuming. So, but they are important reasons why we want to do that. And the 3 most common ones are that we can reduce the residual error variance by improving our model. So very much same way, we are familiar with that from our regression model, right? So by including a second predictor, that's nothing different, right? It's exactly what we are doing. We can increase our model variance. So we can increase the proportion of variance in our dependent variable as explained by our model. So that's accounted for by our second factor, or by our second independent variable. So it is also possible that our hypothesis requires a second or third independent variable, right? Because we know from previous research, or we want to test so whether a certain variable has an influence on our dependent variable. And so another important reason to observe a difference of the factorial ANOVA, factorial designs compared to so the one-way, or like one basically designs where you have only one factor, is so that you can look at how your independent variables interact. So you can look at their so whether the effect of one variable differs across the levels, across the values of the other independent variable, which is very, very frequently the case in real life. So I'd say if so that's one of the fantastic example also from my special textbook. So if we were interested in the effect of hangover, right, that would be our first factor or first independent variable. And let's assume we have two levels. So we say, yes, we are hungover, or no, we are not. And so the second factor would be lecture topic, right? And then again, could be like two levels, so statistics or neuroscience. So in our dependent variable would be the amount of or the time so that students spend sleeping during the lecture. So then we could test whether there's an interaction, right? So whether actually the hangover has a different effect on sleeping duration in a neuroscience lecture versus a stats lecture, right? It might not be the same. So might sleep more or less in one or the other. Okay. Yeah, and so let me just show you the diagram. So right, so here we have a visual display or some illustration of this effect. So here, so we have our first factor, hangover, yes versus no. That's dependent variable, sleepiness. And then we have the two lecture types, the neuroscience versus stats, as separate lines in this plot. And so you can see that, so the difference here in this illustration of the hangover on sleepiness is smaller for neuroscience class than for the stats class, right? So where you are much, basically your sleepiness is much higher if you're hungover. And so there, right? So there, we have talked about that before in regression, just wanted to repeat that, right? So we are differentiating between the main effects. So this is the effect of an independent variable on the dependent variable, and that is averaged across the levels of the other independent variables, right? So here, if we were interested in the main effect of a lecture topic, then we would look at the mean difference, right? So basically, so this is a difference for, so no hangover. This is the difference for hangover. So the main effect would be the average of these two differences, right? So it would be here. And so the same way we could look at the main, so the main effect of hangover across the two levels of lecture topic, right? And then again, so we would take so the mean difference here, right? So in the middle, so that would be our difference, right? So if we would draw, we would basically, oops, sorry about that. So we would draw a line here in the middle, right? And then this difference between yes and no would be our main effect of hangover. So right, and this difference in slope of the lines is a difference between so hangover. So basically, the hangover has obviously a smaller effect, right? So for neuroscience and for stats, right? So that is what defines the interaction. In terms of the sources of variation, so it is more or less the same as for one-way ANOVA. So we are interested, what we are trying to do is be dividing our total variability in our dependent variable, right? And so, and the two chunks that you're already familiar with. So the first chunk is a variance that can be explained by our experimental manipulation. That's our model sum of squares, or model variability. And then the residual variabilities, or our error variance that we cannot explain, right? So that remains unexplained, so by our model. So the difference here is that we are further breaking down the model variance into variability that can be accounted for by our first factor, variability that is accounted for by the second factor, by the second independent variable, and then variability that is accounted for by the interaction between the first and the second factor, first and second independent variable. And then just to, I find it always helpful, right? So then just instead of just using labels or words to also talk about how it's calculated, because it makes things clearer. So the total variability, right? So the total sum of squares is always the sum of each individual score, right? Each score of each individual subject in all groups minus a grand mean, right? Grand mean across all conditions. And so then we have the model sum of squares, the model variability, which is just the sum of each score's cell mean. So that is a cell mean that each score belongs to. So for example, if I'm a student who has a hangover and is sitting in a neuroscience class, right? So then that would be the mean in that cell, that would be so the score. So each score cell mean minus the grand mean, and then takes the square, right, and sum it up. So our unexplained variance is just the sum of each score, so each individual score minus its corresponding group mean, right? So we calculate the square and sum it up. Okay, so the main effect of A, I mentioned that already. So that is, so the main effect of A is the effect that A has on average, right? So we average the effect of A is the difference, if it's like two levels between, so the two levels across all the levels of factor B. So the main effect of B is averaged across the levels of A. And the interaction is just the variation in the effect of A across the levels of B, or the variation in the effect of B across the levels of A. Okay, so here we have so an example with numbers. And so just keep in mind, it's not ideal because that is an example without interaction actually. So here we have only main effects. So we will go through that slowly. I try to color code that a little bit. So so first of all, so this is a simple 2x2 design here. We have two factors, factor A, factor B. So each factor has two levels, and then we have 5 observations in each cell here. And then we can calculate for each cell the cell mean, right? And then we can also calculate the mean for the first level of factor A across the two levels of B. And so for the second level of factor A across the levels of B, and the same thing for B, right, across the levels of A. So basically, so what the sum of squares for factor A is, this is just so here that is this, so that is a variability that can be attributed to factor A. That is just a variability between the, so the group means, right? So between, so if we right, so we take this cell mean and this cell mean, we calculate the average of the two, right? So 2 and 4 are just 3. And then we also take the average of these two, that is 4, so the variability across the levels of factor A, averaged across B, so that is the sum of squares for A, right? And we just multiply that by the number of subjects in each group. Okay, right, so that is our SSA, so our variability that can be accounted for by factor A. All right. So, and then the same way we can do that for B, right? So, so the model variability that is accounted for by factor B, that is just, right? So the that here would be 0.25. That would just be the effect of B, right? So it's across the average across the levels of A. So here it's 2 and 3, so the average is 2.5. Yeah. And here it's 4 and 5, so the average is 4.5, and so the basically variability across the levels of B. So that would be our SSB, right? So again, then we square each difference, right? So for each of the 5 subjects here in this cell, we square the difference and sum everything up, right? So going over these cells. All right. And then we have the interaction between, so let me just highlight all of them. So we have the interaction between factor A and B, and here the interaction is 0. So because there's an so let me start with, so maybe we can, it's always symmetrical, so we can look at it from one direction or the other. Sorry, I have to admit nausea. So, right, if we look at factor A first, right, so then we see that the difference between level 1 and level 2 at factor B level 1 is 2, right? So 2, sorry, it's 1. 2 with a 3 is 1. Yeah, and then at factor, so at factor B level 2, the difference between so the first level of factor A and the second level of factor A is also 1. It's 4 versus 5. So that is exactly what it means to have no interaction. So if I had an interaction, so then the difference would be 1 here, but might be like 5 here, right? So that would be an interaction. That would mean the difference between the two levels is different across the levels of the other factor, right? So, but here it's identical, so it's no interaction. Right, same is true for B. You can check that, right? So here, so the right, so the so for factor B, so it's 2 versus 4, right? 2 versus 4, so it's a difference of 2. It's a first level of factor A, and then it's 3 versus 5, so also 2 at the second level of factor A. So again, no interaction, right? So otherwise it would have to be, I don't know, 2 and 0 or 2 and 10. I hope that makes sense. So in this case, we have no interaction, yeah? 0 interaction. So only main effects. So the effect of one factor is constant across the levels of the other factor. So how to determine the degrees of freedom in our factorial ANOVA? So for the total sum of squares, so we already talked about that, right? So it's just a number, it's basically the total number of subjects minus 1, right? So it's a 1 degree of freedom we're losing because we are estimating the grand mean, so across all observations. So it's just the number of observations within each cell times the number of levels of each condition. So it's a P times Q, right? It's just the number of cells that we have. So then for our model variability, so that is the degrees of freedom obviously are the number of cells that we have, so or also called the number of conditions, right? So in the 2 by 2 example, it would be 4, so 2 by 2, right? So 2 times 2, 4, and then again we have to subtract 1 because we are calculating the overall mean, right, across the different conditions. And so for our residual degrees of freedom, so we're losing, so it's it's again, so the number of cells, so the number of factor level combinations times the subjects or the number of observations within each cell minus 1, right? Because it's a so there's basically deviations from the mean of each cell, right? So we're losing 1 degree of freedom for each cell by estimating the mean for it. And so for our first level, right, it's as usual as we know from the one-way ANOVA, so that's just the number of levels minus 1. So similarly for the second factor, number of levels minus 1, and for the interaction, it's so of the two factors, it's just the product, right, of these 2 degrees of freedom. All right, so. Right, and then so always check, right, whether it's all correct. So the total degrees of freedom, of course, is the model degrees of freedom plus the residual degrees of freedom, and the model degrees of freedom is the so the degrees of freedom for each individual factor plus any interactions. And so if we have more factors and more interaction terms, so they all add up to the model degrees of freedom. Okay. So of course, so in a factorial ANOVA, we in most cases we want to test both the main effects and the interactions, unless we are very sure and can be very certain that there are no interactions. And so a main effect, right? So this, in the same way that we discussed main effects and regression, a main effect test just determines whether the cell means significantly vary across the levels of a single factor. Right, so whether in our my fantastic example was the sleepiness, so whether the sleepiness, for example, is different in neuroscience versus statistics class. So that would be the main effect of lecture type. And so the main effect of hangover would be whether the mean sleepiness is different between, so if I'm hungover or not, right? And then, as I said, so we would average across the other, the levels of the other factor. And so the test statistic for the main effect of so factor A is just the variance of level means for factor A. So it means, right, it's our mean square measure for factor A, right? And that is sum of squares A divided by degrees of freedom for A, as we just discussed, and divided by the residual variance. So very much what we have already discussed for the one-way ANOVA. It's exactly the same, right? So, and so accordingly, so test statistic for B is just the mean sum of squares, so the mean squares for B divided by the residual mean squares, right? So also the same as for one-way ANOVA. The only difference here is that it's not the model mean squares, because we're breaking down the models mean squares, and so look what we can attribute to factor A and what we can attribute to factor B. And so finally, so the interaction is just so the variance of the cell means that is not accounted for by either factors A or factors B. So basically it's everything that is left in the model variability. So that is not, so after subtracting, so basically if we have the model sum of squares, right? So then we are just subtracting. So the sum of squares for factor A, sum of squares factor B, and whatever is left over, that is our sum of squares for the interaction term, right? And so we also test as a test variance is also residual variance here. So basically it's all similar to the one-way ANOVA. So our test variance, we're all testing that against the residual variance that is not accounted for with a model. We're just breaking down the, so the model variance into its different components, right? And the two main effects and the interaction term. And the same is true if you have like a model for that has more than 3 factors, right? So you do that in the same way, just that your model is more complex and you're breaking down it into like 3 main effects and then potentially 4 interactions, right? So if you have three factors, then you can have 3 two-way interaction terms and 1 three-way interaction term, but so the logic is exactly the same. So I just wanted to show you, so because it is often mentioned also in textbooks, and it's important when you interpret your own data. So what patterns of interactions you can come across. So when you obtain a significant interaction effect. So, and it's important in terms of how you interpret your main effects, right? So here on the left side, so the left panel has, okay, let me start over. So the way as the data is displayed here is that we have, one factor with 3 levels, right? That is shown, so basically it's shown here. And then there are different lines for, so the second factor that has 2 levels, B1 and B2. And here on the left hand side, so we all have cases where there is no interaction between the 2 factors, right? So here we have only, under A, we only have a main effect of factor B actually. So we see that between B2 and B1, there's a difference, but we do not have a main effect of A. You can see, so that the means for across all levels of A are constant, right? So there's no effect, no differences so no significant main effect of significant, we don't know, right? It's just a graph here. So there is no main effect of factor A, there's only a main effect of B. So here, so we do have a main effect of A and B, right? So we still see there's a difference between B1 and B2. This difference is constant across all levels of factor A. But in addition, we see some variation in the means for factor A, right? So we see that A2 is smaller than A1 and A3. So here we have a main effect of factor 1, 2. So it's 2 main effects, right? But no interaction. So the pattern, so the differences for A look exactly the same for B1 and B2, right? And the same, so the difference between the levels of B look identical across all levels of A. And then finally here, so we have again a main effect of both factor A. You can see, right, so that A1 is smaller than A2, smaller than A3. And we also have a main effect of B, right? And again, no interaction, so effect of B is constant for A1, for A2, for A3, and the effect of A, right, you see these parallel lines, is constant across all levels of B. Okay, yeah, so difference is always between A1 and A2, and A1 and A3, and A2 and A3, so these differences are identical for B1 and B2. Here, so on the right-hand side, we see different patterns of interactions. So so here, basically, we see that the two lines cross. And if that happens, so it is not very meaningful to interpret your main effects, even if you get main effects. So here you're probably, if your data look like that, so the main effect would be 0. Right, so for both, because if you look at it, right, so the difference between A1, A2, and A3 for B1 is exactly the opposite of the difference between A1, A2, and A3 for B2. That means if we would average across the three, so across B1 and B2, then you would end up with 1 point here, right? So 1 point here and 1 point here, so that would be a horizontal line. So there would be no main effect of A, right? In the same way, that will also not be a main effect of B, because if you average across the sorry, so let me so did I explain it the wrong way around? That doesn't matter. So if you basically average across the three levels of A, right? So then so the resulting value, no, I did it in its correct way. So the resulting value is exactly identical, right? So for B2 and B1. If you take the average across these three levels, so and across these three levels, so then you will end up with this value here. So that is a case where you have only an interaction but no main effects. So here you also have, so whenever the lines are not parallel, right? So then there's an interaction. So you also have an interaction. And so you have to be cautious, right? So when you interpret the main effect, because so you can see, and here you will probably, so if you, for example, if you're interested in the main effect of B, so we see that on average, right? If we average across all levels of A, so we see that so B1 is a bit higher than B2. So that would probably give us a main effect. But we can see that actually B2 and B1 differ only for A2 and A3, whereas there's no difference for A1. So we have to take that into account, right? So whenever there's an interaction, so we have to check whether, and we have an interaction and main effect, so we have to check whether the main effect is actually there across all levels of the other factor, right? Or whether there are certain levels that do not show this main effect. And the same is true for A, right? So we see a main effect of A, so we see a difference for B1, but we do not see the difference for B2. So it means you have to be cautious. So there's no like a general main effect, right? So only on certain levels of the other factors there's a difference. And so it's basically the same thing here. I don't go over that again. So the only difference is that so here, so you basically have so if you're looking at the main effect of B, so we see that B1 is always smaller than B2. Right, so it's just the magnitude of the difference that varies across the levels of A, right? So it's largest for A1, then it's medium-sized for A2, and smallest for A3, but A3 still shows the same trend, right? So the same direction of the effect. So this is just to illustrate, right? So that whenever you find an interaction, it's very important to plot your data and to understand your interaction and to make sure you interpret the results correctly. So sometimes they're classified, those interactions, right? So that they're called ordinal if the lines do not cross, right? If you plot them, then hybrid if they only cross for one way of plotting them, right? So either B is a function of A or A is a function of B, and disordinal if so in both ways of plotting result in this crossover here. Just wanted to include that so that if you ever come across those terms, so hybrid or ordinal interaction or disordinal interaction, so that's what is meant. And it's basically just referring to the same thing that we just talked about when we were looking at the other slide. Okay, so let's talk about, or let's go over a concrete numeric example. So here, so that's an example for a two-way factorial ANOVA. So it tests the effects of alcohol. So that's the first independent variable, so first factor, and gender on the beer goggles effect. So that means how the perceived attractiveness of other people changes depending on how much alcohol you have consumed and what your gender is. All right. So, and so as I said, so the first independent variable, the first factor here in this example is alcohol. So it's either none or 2 pints, but this 4 pints, so I had 3 levels. And the second independent variable, second factor is gender. So here, male and female. And then, so the dependent variable is an objective measure of the attractiveness of the partner selected at the end of the evening. Okay, good. So how meaningful that example is, but it will show our point. All right, so here are the data. So we have 6 groups of subjects, right? So, so we have a 3x2 design. So 6 groups of different subjects. So males and females who had either none or none. So I had no alcohol, 2 pints or 4 pints, right? And then we see in each group we have 1, 2, 3, 4, 5, 6, 7, 8 observations, so 8 subjects, right? And they're all different subjects. So these are different females than those and then those, right? So the males also are all different. Okay. Right, and then we can calculate the mean of all scores, or a grand mean, regardless of group membership, and that is for this example 58.33. So that's our grand mean, right? So if we're now were to calculate our total sum of squares, so we are just subtracting so the grand mean from each individual score, and then we calculate the square of that value, and then we sum it up across all observations here, and then we end up with this value, right? So, and then we are interested next in calculating the model sum of squares, right? If we wanted to do ANOVA by hand, which is actually not that hard to do, just a lot of calculations. So now, so we're interested in the so what we are putting into our calculations is each score cell mean. So that means that's the mean, right? So of each group that an individual participant belongs to, right? So for the females that had no alcohol, the mean would be 60.625. For the males that had no alcohol, would be 66.875, et cetera, right? So, and then for each participant, so we are taking this mean value, right, of the group that they belong to, and calculate the difference between the mean and the grand mean, right? And then again, we take the square and sum up across all our participants. Okay. And then we come up with, these other calculations. I'm not going over that in all detail, but that here would be our model sum of squares. All right. So, but it can be very so informative to try to basically to go over that yourself and check the individual steps, so it helps you understand what we are doing when we're calculating in ANOVA. So if you're calculating sum of squares, right? So And then, so we are now interested, right? So after we have calculated the model sum of squares, we want to break it down a little bit further and we want to say, okay, what is the sum of squares that can be attributed to alcohol? So variability that can be attributed to alcohol. So now we are collapsing across gender, right? So now our groups are, so males and females collapse, right? So, and now we're calculating the mean for no alcohol, the mean for 2 pints, and the mean for 4 pints, right? So across both genders. And again, so we subtract each score, factor level mean, and so we subtract the grand mean from each of these factor level mean values, right? So for each individual participant. And then we come up with this value here, right? So that would be the variability due to alcohol, so different amounts of alcohol consumed. And then finally do the same thing for gender, right? So now we are collapsing across the alcohol conditions. So first, we're interested in the mean effect for so the mean, right, attractiveness rating for females. So across the 3 alcohol conditions, right, which is 60.21, right? So we are averaging these 3 columns here. Right? And then we do the same thing with males, right? So we're averaging across these 3 columns here, so to come up with a mean effect for male. And then, so basically the way we're calculating so our sum of squares the same way we did before, right? So we are subtracting, so for each individual is subtracting this mean and the grand, so we're subtracting the grand mean from this factor level mean. All right, so right, that's what we're doing here. Yeah. And then we come up with this value here, right? That's the sum of squares for gender. Okay, and as I mentioned earlier, if we are interested in the sum of squares with interaction, we don't have to do that much math. no summing up anymore, it's relatively easy. So in order to determine what the sum of squares with the interaction term is, we just take the sum of squares for so the model sum of squares that we had calculated earlier and subtract the basically alcohol factor sum of squares and the gender factor sum of squares, right? And so whatever is left over, whatever is not explained by these 2 factors is so the variability due to the interaction of the 2 factors, right? If there was no interaction, so then that so that term would be 0. Right? So here it's almost 2000. Okay. All right. And so the residual sum of squares is just so basically we're taking each individual score and are subtracting their the corresponding group mean, right? So corresponding cell mean. So for 65 minus 60, 0.625, 70 minus 60, blah, 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 right? We calculate the square and sum it up. So that's our residual sum of squares. All right, super. And after we have calculated all these sum of squares, so we can also determine our mean squares for each of these variance components. So we know degrees of freedom, so model degrees of freedom are, not the model degrees of freedom, but the degrees of freedom for our first main effect are the levels of that factor, -1. So alcohol has 3 levels, -1 is 2. Gender has 2 levels, -1 is 1, right? So, and then we are just dividing the sum of squares by the corresponding degrees of freedom. And so that gives us our mean squares, right, for the 2 main effects. And then we're calculating our F ratio by dividing the mean squares for also the main effect by the mean squares of the residuals, right? And so residuals, right, so it's the degrees of freedom is 7 times 6, so we had, right, so that is just number of participants in each group, 8 minus 1 times number of cells, and that is 42 here, right? So, and so our interaction is just basically, so the degrees of freedom for the interaction is just the degrees of freedom for the 2 main effects multiplied, so 2 by 1. Yeah, and then so we are basically calculating our F ratios just as as a ratio of the mean squares of the main effects, residual mean squares, and the mean squares for the interaction is the residual mean squares. So, okay. So of course, so you wouldn't be surprised that the two-way ANOVA can also be framed or expressed as a multiple regression analysis. So it's nothing else, right? It's just multiple regression with categorical predictors. And then we have to do some sort of coding again, right? So to include our predictors, our independent variables in our model. And here that's an example from the textbook where so they were comparing the political ideology values that was on some scale from 1 to 7. So I think 1 being most liberal and then 7 being most conservative. And so one factor one independent variable was party ID. So whether somebody is Democrat, Independent, or Republican. And then the second factor here was sex, right? So whether somebody male or female. And so this is the, right, so the political ideology is a dependent variable. So again, so we are friendly here and assume that they're right, so that it's interval scale level, so that's actually okay to calculate the mean, right? So for these ratings, so let's assume that is true. Always don't like these examples from rating scales because they're, I think it's not appropriate, but anyway. Okay, so then let's see how we can express that as a regression model. So it's basically the same thing that we did for our one-way ANOVA. We just have to do a little bit more coding, right? So we need more in this case, dummy variables. So we have talked yesterday about other ways of coding. So here we will just go over the dummy coding because it is exactly the same as for one-way ANOVA otherwise. So let's assume, so we introduce first a dummy variable for political party ID and the second one for sex. So the first dummy variable is called P and the second one is called S, right? And then so we have P1, that is basically our dummy variable that codes if somebody is Democrat or not, right? So it's 1 if somebody is a Democrat, and it is 0 otherwise. And then we have the second dummy variable that codes for party ID, and so this variable is 1 if somebody is independent, and it's 0 otherwise. And then, so just remember, we don't need a third dummy variable because Republicans are just defined as the ones who are 0 on both P1 and P2, so on these two dummy variables. Okay, so how about the dummy variable for gender or sex? So that is easier. Here we need only 1 because so sex has only two possible levels. But here, so 1 is just used to code female and 0 is used to code male. So more we don't need, right? And then we can write down our regression model. Assuming there's no interaction, right? So we can just write down our regression model as usual is alpha plus beta 1 times P1 plus beta 2 times P2 plus beta 3 times S. So very much the same way as I did before. And in order to find the correspondence between our population means and the regression parameters, we simply substitute the possible values for the dummy variable. So it's really easy, right? Because the possible values are just 1 and 0. And that's why, so the regression equation is much simpler, right? If we really substitute the possible values. Yeah, so just for illustration purposes, so for Republicans, right, are 0 on both dummy variables that code for the party ID. So the mean political ideology is simply, right, so alpha plus beta 1 and then times 0. Plus beta 2 times 0 plus beta 3 times 0. And that is just alpha. So that means that alpha, so our intercept, is in this case, so if we code our categorical predictors like that, then our intercept for the regression model is just the mean, mean political ideology for Republican males, right? So for Republican females, so again here S is 1. So the mean ideology is alpha plus beta 3. So that means beta 3 in this case indicates a difference in mean ideology between male and female Republicans. Yeah. Okay. So if you do that for all other combinations that we can see, right? So that's shown here in this table. And you can see that male, so for basically that beta 1 is just a difference in political ideology between male Democrats and male Republicans. Beta 2 is a difference between male Republicans and male independents. And then we already talked about that, right? Beta 3 is a difference in political ideology between female Republicans and male Republicans. And then, so the other two means, so they're basically a little bit more, right? So they're combinations of these effects that we just expressed. Okay. Yeah, then so our population mean is just all effects added together, obviously. Right, so this is a regression model, right? So that would be the mean for our Republican males. And then again, so that is the difference between the Democratic males and the Republican males. That's a difference between independent males and Republican males. And that is a difference between Republican males and females, right? So this coefficient here. And so our output looks exactly so the same as we're used to. Right. So we can see that basically, so the first, I'm not sure what software created that that output, but we can see that everything is significant except for the difference between the two genders. So that means that actually, the Republican and the males and females do not differ, right? But that is assuming there's no interaction. Okay, so what about the interaction? So what if we want to include an interaction in our regression model? So that's also very easy. So we just do the same thing that we did for our regression models with continuous predictors. So we are just multiplying our predictor variables, right, to form the interaction terms. So in order to to include a two-way interaction of party ID and sex, we just form the cross products of our two dummy variables that code for party ID and our one dummy variable that codes for gender or sex, right? So because, right, it's just with continuous predictors, we had only for two-way interaction, we had only one cross product, because so each each predictor had only one coefficient. But here, because of the way we are coding our category predictor, so party ID is actually coded by two predictor variables, so P1 and P2, and therefore so we have two interaction terms rather than only one, right? Because we have to multiply both of these indicators, these dummy variables, with our dummy variable for gender, right? If gender had more than two levels, so that would be even more complex, right? So we had to basically add any possible combination. Okay, so but here it's only P1 times S and P2 times S, and they are like new additional regression coefficients, right? And so then B4, not B4, but beta 4, if it's like the population regression coefficients, reflects the difference of Democratic versus Republican voters, or like members, people identify as Democrat versus Republican. So the difference in their ideology among males versus females. So basically, how do so how does the difference in the ideology between Democrats and Republicans differ across females versus males, right? So is there maybe a smaller or larger difference between Democratic and Republican women as compared to Democratic and Republican males? And beta 5 reflects the difference of independent versus Republican among females versus males. So it means is that contrast, right? It's a difference in political ideology in our dependent variables. Is a difference between independent and Republican. Is that difference different for males versus for females versus males? Okay. And then so for our F-test, so we basically so if we want to test whether it's an interaction or not, so we're testing the null hypothesis that these two coefficients that code for this interaction are 0, right? And so that means we're just, and that is what we are doing when we're testing the interaction mean square, so divided by the residual mean square, right? So we're testing this at beta 4 and beta 5 are 0. Okay, so here, so that seems to be the case. Right? Okay, so the assumptions are the same as for the one-way ANOVA, so we don't have to go over those again. And if you want to fit in a factorial ANOVA model in R, so it's not much different from what we have done for so the one-way ANOVA, just a little bit different in terms of interpretation. So it's always a good idea to set the contrast coding scheme beforehand. So I mean, of course you always have the option to set your contrast individually for your specific model that you're fitting, right? So with the basically you setting this attribute contrast, right, for your factor, for your independent variables. But you can also set a default, right? So then R will automatically apply the same contrast coding schemes to all models you're fitting, unless you tell R to do anything else. And in order to do that, for example, if you wanted to set the contrast coding scheme for unordered factors to effect coding, right? So just a reminder, yesterday effect coding, there was this deviance contrast that was basically the coefficients express the difference between the mean of each individual group and the grand mean, right? So in effect coding, so the regression coefficients reflect the difference of the individual group means from the grand mean. Or some other sum to 0 contrast, right? So you can use Helmert or whatever you prefer. And then for the ordered, so you can use polynomial contrast, but that's a default in R anyway. So it's just basically to show you how you could set that. So use it using the function options. So, and that is basically to change the default way that R handles and codes contrast. If you want to do that, right? So if you say, well, I want to have the same kind of contrast for all the models that I'm fitting today. So I'm just setting that via options. Okay, so and when you're fitting factorial ANOVA in R, so you can also, I mean, there are always multiple ways to do it. And so there are more ways as a tutorial. I'll also include, so there are also more ways to look at your effects in the Markdown file. I just wanted to show you one of the options that we haven't discussed so far, and that is the ANOVA function from the car package. So note here that it's not a typo, it's really capitalized, so that's a difference, right? So it's part of the car package. So it's as I said, ANOVA capitalized. We also have the lowercase ANOVA function, right? So, but that's a different one here. And you can use that with your, so for basically to show a summary of the results for a model that you fitted using LM. Right here, so it would be attractiveness, right? So that is our dependent variable. And then, so the syntax for the model specification is the same as for regression models, right? So that just means it's a shortcut for gender plus alcohol plus gender times alcohol. So you can just type gender times alcohol, and then R will do the rest automatically. Assume that you also want to test the main effects. You have to specify the data, and then what type of sum of squares you want to use. And that is important because R uses as default 1. Yeah, so otherwise it will use type of squares 1. And so was it 2? Oh, I'm not 100% sure. It's in the tutorials. I keep forgetting because I rarely use it. I'm not 100% what the default is, but it's not 3. And remember, so we were talking about that it has been a while. There's a longer statement, will be a longer statement in the or example in the markdown file. So type 3 is the safest option if you don't have any reason to assume otherwise. So type 2 is actually, so okay, let me just repeat that. So you should always, if you for whatever, if you don't know exactly what you're doing, so you should always go for type 3. Right, so and you have to specify that because otherwise R will use a different default. R doesn't have type 3 as a default. So other software packages like SPSS have type 3 as default. So you don't need to worry about that. But for R, you have to. And so type 2 makes only sense if you're 100% sure that there's no interaction. So then type 2 is more powerful, but otherwise don't use it. And type 1 is basically this hierarchical regression approach, right? Where you do this stepwise. So hierarchical model building depends on the order of your factors. So that is also only meaningful in certain cases, and don't use it if you're not sure whether it's correct or not, right? And then also just a reminder, you have to worry about the type of sum of squares only if your sample sizes are unequal. Otherwise, it doesn't matter. Otherwise, it's the same. So if you just use as a default type 3, you won't err terribly, right? So that is basically you won't make a horrible mistake if you just use that as a default, even if your design is balanced. Okay. Right, and then so you're getting the typical ANOVA output if you use the ANOVA function. So right, as it's your effect of gender. So that's a grand mean. Here's the intercept. So then you have your effect of gender. You have your effect, so main effect of alcohol, right? And so these are the corresponding F values here. And then you, these are the sum of squares. These are the degrees of freedom. These are the corresponding F values. And that is your P value, right? And we see that there's no significant main effect of gender. We saw that earlier already from our regression model, right? And you can also see the P value is the same. But there's a significant main effect of alcohol. So that means alcohol, so whether you have 0 or 2 or 4 points, it changes the attractiveness ratings. And there's also an interaction. So that main effect of alcohol differs for men versus women. Yeah. Okay. So if you have a significant overall ANOVA, so you may want to do post hoc comparisons, right? So here we have so a main effect of alcohol, and we also have this interaction. So we want to take a look where these differences come from. And so again, the same logic as for the one-way ANOVA. So the way you do it is exactly the same. You can use so the post hoc test function from the DeskTools package, and so you just specify what correction, what adjustment method you want to use. And so for our example here, you will first get the differences for the factor gender. That means you get the simple comparisons between males and females. So again, so that is basically that's the mean of males across all levels of alcohol. The mean of females across all levels of alcohol, right? So the difference is 3.75. That means attractiveness for males are 3.75 points lower than for females. But again, so it was not significant, right? And then you have the comparisons for alcohol, right? And there, because it's more than two levels, you have three levels, so you have three comparisons, right? It's 4 versus 2, none versus 2, and none versus 4, right? And you can see that the difference, so there's a significant difference between 2 versus 4 and none versus 4, but so none versus 2 does not result in different attractiveness ratings. So it's actually really the 4 points that appear to make the difference. And then, so if you do the post hoc test for your 2-way ANOVA, so you get also so the what is called the simple comparison. So that is really the comparison of each individual cell, right? So the means for each individual cell. So we had 6 cells in total, right? So 2 times 3, so 2 genders, 3 levels of alcohol. And then you really do all the pairwise, so it's really all the pairwise and comparisons that are included here. And we can see that, our highlights, what's significant with stars. So you see that for males, so you have this, so that male 4 pints differ from females 2 pints, male 4 pints differ from male 2 pints, male 4 pints differ from female 4 pints, and female none differs from male 4 pints. Not surprisingly, male none also differs from male 4 pints. So it's really male 4 pints that seems to be quite different from the rest, right? So if you wanted to do orthogonal contrast, you could do that, of course, as well. And so in order to code the contrast for factor alcohol, we use the same coding scheme that we discussed yesterday. So here, no alcohol would be like a meaningful baseline, right? So that we want to maybe set up a first contrast where we are comparing no alcohol with alcohol. So right, we're setting that to -2 and these both to 1. And then second contrast might be whether the dose of alcohol, right? So the amount of alcohol makes a difference. So that's contrasting 2 versus 4. And for gender, we have only 2 levels. So the only possible contrast is 1 and -1, like here. Okay, so, and then you define your contrast. You set the contrast very much the same way as you did that for the 1-way ANOVA. You fit the model. And so then you get the results, right? So for your predefined contrast. So now, so your facts are coded in a different way, right? So the way you define by your contrast settings. And so again, we can see that, not surprisingly, right? So gender is not significant. I mean, how would it? It wasn't in the previous analysis, and so because gender has only 2 levels, doesn't matter how you specify. So the contrast is always the same. And then for your so the first contrast, so that is no alcohol versus 2 or 4 pints, right? So then again across the levels of both levels of gender. You see that is significant, and so 2 versus 4 pints also significant difference. And then you can see that these contrasts here differ across men and women. So that means the difference between so this alcohol 1, right? So it was our first contrast. So the difference between no alcohol versus 2 or 4 pints, right, combined. So that's basically no alcohol versus alcohol, this contrast. That differs between men and women. So that means the difference between no alcohol and alcohol is different for men versus women, right? So in here, also the second contrast, so the difference between 2 pints versus 4 pints, that also differs for men versus women. Right? So that is just if you want like an all-in-one output, right? So I won't go over that, it's just FYI here. So, all right, yeah, if you don't want that separate, if you want all the, so the main effects, interactions, the contrast, etc. So you have to do it like that. This is the list command again. All right, so, and this is, as I said, if you have a significant interaction, you always have, generally, right? We plot our data, but so if you have a significant interaction, it's really important to plot a log to understand what's going on. So first, so this is an illustration of the main effect of alcohol, right? So these bars here represent so the mean attractiveness ratings collapse across genders, right? So that's for none, for 2 pints, and then for 4 pints. Okay. And so that we see that the basically after having 4 pints as a selected partner was less attractive, right? So, so this is the gender, the main effect of gender. We can see that there's not really a difference between men and women. And so here is so an illustration of the interaction effect, right? So so here on the bottom we have the different levels of alcohol. So no 2 pints versus 4 pints, and then we see that for females versus males, and that clearly shows where the interaction comes from. So for females, we basically see that this makes almost no difference, right? So how much how much alcohol a female drinks in this pseudo data set here doesn't really has an effect on the attractiveness rating, right? So if all, then maybe this, but so that's basically almost nothing. And we already saw, right? We saw in our simple comparisons, if you go back to the slides, sorry about that. So that for females, so the contrast between 2 pints and 4 pints was not significant. Let me find that female 4 pint, yeah, so here, so that's a difference, right? Female 4 pints versus female 2 pints, that was not significant. And so we can confirm that here, go back, right? So that's basically, that's identical. However, so for men, so the difference between no and 2 is also non-existent, but then so it really plummets for 4 pints. So suddenly here we have this huge drop in attractiveness. So, right, and that is what drives the interaction. So what accounts for the interaction. And that also drives the main effect of alcohol, right? And here we can see how it can be misleading to interpret the main effect in the presence of a significant interaction. Because if we would say, well, if we had 4 pints, so we choose less attractive partners, then so that is not necessarily true, because it's only true for men. It's not true for women. Yeah. Okay. And then these are just different ways to illustrate the same kind of findings. All right. Effect size. So effect size is the same as for one-way ANOVA. So just we're breaking down the effect sizes for main effects and interactions now, but the effect size measures are exactly the same, right? We have our eta squared and the omega squared. Eta squared is biased. Omega squared tries to correct for this bias and estimate the true population effect sizes, right? So it's always preferred. And so we're basically calculating that for our individual effects, right? Or the interaction. So it would be the same for B, right? So the main effect for B would be SSB divided by SS total. And yeah, I mentioned that earlier, right? Okay, so that much. So for our factorial ANOVA. And so now switch gears a little bit and talk about repeated measures ANOVA. And so it's just a general reminder, right? So the repeated measures design is one in which we have the same subjects or observation units that are measured multiple times. So these multiple times can be under different conditions or simply at different time points. Yeah? So, but the decisive part is that we have the same observation units, the same subjects that are measured multiple times. Yeah? And therefore, we can view the repeated measures ANOVA as an extension of the dependent t-test, yeah? So which involves only 2 related measures if we have more than 2 measures, if we have more than 2 conditions. Okay, and so the main difference and why that requires a special treatment is that so unlike the regular ANOVA, so factorial ANOVA, one-way ANOVA, our observations are no longer independent, right? And I talked about that in great length, how independence of the observation is an assumption of our model and the correctness of our statistical tests. So for repeated measures designs where we have, so we observe the same subjects over multiple conditions or time points. So our observations are not independent. So we are in violation of the model assumption. That means we have to do something about it. Okay. So, right, so this is just an illustration. So it could be either different time points, right? So we're investigating the same people, same group of people. So here, so we're measuring the blood pressure at multiple time points, right? So it could be across times of the day, right, and always the same participants. Or we observe so the same subjects under different conditions. So for example, what is the best chocolate cake? And then we have participants taste what is the best cake. So we have participants taste chocolate cake, caramel cake, and lemon cake. And they have to rate so how tasty it is. Okay, so for the repeated ANOVA, so the repeated measures and analysis of variance. So the breakdown of our variability is different than for our factorial and one-way ANOVA. So we start again, so with the total variability, right, and break it down into, so now instead of breaking it down into model variability and residual variability, we break it down into between subject variation and within subject variation. And then so basically we are just focusing on the within subject variation and break that down further in our model variability and our residual variability. That means we are completely ignoring any so basically is a variability that is due to differences between our participants, right? So between subject variability that's completely outside of our model here, and that has certain benefits. So as we will talk about in a second, right? Okay, so right, that is just here. So the between variability is between our subjects. Basically how different, so we could see that as a sort of a baseline level. So right, so we for our cake example here, or it's a blood pressure example, right? People might just differ in their general, so person A might have generally a higher blood pressure level and person B, etc., right? That means probably across all the time points, their blood pressure levels will be higher. So irrespective of the specific fluctuations, right, across time. And the same here, so person A might generally like cake much better than person B, so the ratings will be much higher because they're a cake fan, whereas person B is like a meat lover, right, doesn't like cake. So, and that is what is meant by between subject variation, right? So these differences in sort of baseline between participants. And then we have the within participant, so basically we have two parts, right? So two sources of within participant variability. So this is a variability across the so our levels of our factor, right? So it's across the repeated measures for a given participant, right? So the rating for cake A versus cake 2 versus cake A, B, or C. And we have our within variability across levels that is not explained by the mean differences between the factor level, and that is like some idiosyncratic variability, right? So there's just some idiosyncratic pattern of change for a given participant across the levels. So yeah, to make that clearer, we'll talk about that in a second, but so in general, so maybe with the cakes, not as intuitive. But so let's assume so the plot there was a clear pattern across all participants that the blood pressure would rise, right? That would be lowest in the morning, the highest at noon, and lowest at 3 p.m., higher at 5 p.m., and then highest at 8 p.m. And so let's say on average, so the difference would be, I don't know, yeah, 10 points here between time point 1, 2, and 3. So then participant A might have a difference of 5 between point 1 and 2 and a difference of 20 by point 2 and 3. And so this deviation from the average of difference 5, right? But that would be idiosyncratic residual variability that cannot be explained by our model. So that is the error variability in this model. Okay, so so let's again do that with numbers to make it a little clearer. So we have our total variability, right? So total variability is just the so we can calculate the grand mean, right? And it's just how much each individual score deviates from the grand mean. And so then we have our between participant variation, right? So we can calculate for each participant. We can calculate an average across all conditions or all time points. And so for our first participant here would be 4, 3, 2, and 7. So then this variability, right? So the variability of the individual averages from basically deviation from the grand mean. So that would be our between subject or a variation that we are completely ignoring in that design. Okay, and so we also have our so we have the within subject variation, right? So that is so the within subject variation is just it's basically the deviation of the individual scores from the as a condition means, right? So and the so what is the model variability in this design? It's just the condition, basically the variability across the condition means. So right, so the difference between here 2 versus 4 versus 6, right? So it's a blood pressure example, right? So it might be lowest blood pressure, a medium blood pressure, highest blood pressure. So across all participants for these 2 time points. And then we have the so the error variability, and that is this idiosyncratic pattern that can not be explained so by our model. So in this case, it would be 0, by the way, right? So here you can see that for each participant, again, it's only fabricated data, maybe not the best example. So that right, so on average, the difference between condition A and B is 2. And you can see that it's true for each individual participant, 2, 2, 2, 2, right? And here's the difference, also 2, and you see that's also the case, right? 2, 2, 2, 2. So here in this fake data example, so the residual variability, the error variability would be 0. Yeah, so because that all individual differences correspond to the mean differences. Okay. So there's several benefits to repeated measures design. So the first one is that any basically within group variability, right, is accounted for, and we can thus eliminate that as a source of residual error variance. So basically the differences between participants, we can just forget about them, right? Because of the fact that we are observing the same subjects across multiple conditions, we can estimate, basically, what is the what are the baseline differences between our subjects, and then we can kick them out, right? And say, well, that we are not interested in that. So we are only interested what is the variation across our conditions, right? And so another huge benefit of a repeated measures design is that because we're observing the same subjects across all conditions, so we don't have to divide the sample size by groups, by the number of groups. That means we don't have to have like, I don't know, like 30 units or 40, 50, 60 observation units in each cell of our design. We can just have like 100 and test them repeatedly. And then depending on the complexity of your design, that's a huge difference, right? So you can save a lot of time and money. And so it also means it is more powerful, right? If you're using the same sample size, so if you're working with the same sample size overall, if you say, well, so all I can test are 100 subjects, I cannot do more because of certain limitations. Then of course the within subjects design is much more powerful than the between subjects design. Okay, ma'am. And this can be a big issue, especially if you have hard to reach populations so that are difficult to recruit. Of course, that all comes with so some costs, and so due to the fact that we're observing the same subjects, the same observation units repeatedly across multiple conditions, that we can have, if it's like humans, right, so we can have facts like fatigue, repetition, or all sorts of other crossover effects, right, due to the multiple measurements. And that's always important to keep in mind. All right, so again, so this is how we calculate our sum of squares in the one-way repeated measures ANOVA. So the total sum of squares the same way as we had calculated them before. So the between participant variation is just the mean of each subject, right? It's the mean across all levels minus the grand mean, right? And then we multiply that by P, so the number of levels. And then for or within subjects variation, we take the sum of each score, each individual score, minus the mean for this particular subject across the levels, right? So that means as we take the individual subject score for a certain condition, and then we subtract so the mean for this particular subject across all levels from the score, right? We sum that up. And we can further break that down, right, in the residual variability and the model variability. So here, so the model variability is just each level's mean. So here the mean is across participants, right? So we're taking the mean of each level of each condition across all participants and subtract that from the grand mean and sum it up, right, after calculating the square. And then the residual variability is just the within participant variation minus the model sum of squares, right? So minus the general pattern, right? So if you see that as a, so you can always see that as a profile, right? So you have a general pattern of change across the conditions, right? So it might rise or might fall across conditions. And that is our, right, that by averaging the pattern, so for all participants, we get this general trend. And then so the error variability is the individual deviation from this trend, right? And so we have to keep in mind, sorry, that I wanted to add that, so this residual variability is, so you can see that as an induction, so basically that there are two components to it. It's an induction of the subject in a particular condition, right? It might just be like a, not like just random error, but it might be something idiosyncratic. So for example, in our cake example, it might just be the case that one person really loves chocolate, right? So more than, so that because they love chocolate so much, they say their rating for chocolate cake is 5 times as high as for lemon cake, whereas on average, so the rating for chocolate cake is only twice as high as for lemon cake. So it's because this person is such a chocolate lover, but that is not right. So that is that might be an interaction of subject and condition, and then it might be in addition to any random error that might happen to so the unreliability of the measurement instrument or some right. Whatever. Huh? So it's just important to keep that in mind. All right. Okay. So for the degrees of freedom, I mean, that is just, of course, we also have to split the total DF into 3 parts, one for each source of variation, right? Makes sense. So the total degrees of freedom is the same as for our general ANOVA model, right? So then the degrees of freedom for between participant variation we're not interested in. But it's also equivalent to, so it's basically just the so the number of subjects minus 1, right? So but it's equivalent to what we're dealing with in the one-way ANOVA. And so then we have the degrees of freedom for our within subject variation. So where we're losing 1 degree of freedom for each level, right? So because we are calculating the average across all levels for each individual participant. And so here for the effect of the experiment as a model, degrees of freedom again, we are losing 1 degree of freedom by calculating the average, so the grand mean across our levels, the numbers of P levels, right? So the number of conditions. And then this is just the product, right, of our that is just the product of our between subject variability and our model. So the degrees of freedom for our between participant variation or model variation, because of course we are estimating both so the right, so the mean for across the conditions, and we do that for each individual subject. So that's why we're losing 1 degree of freedom for each factor, we can call it, or source of variation. All right. So, and then the general F-test is calculated in the same way as we do that for our ANOVA, right? That's the mean sum of squares model divided by the residual mean sum of squares. Yeah, so this divided by this. Okay, so assumptions are mostly the same as for so regular ANOVA. The only thing that's different is that we have one additional assumption. So for this, some assumption is called sphericity. So in order for sphericity to be an issue, we need to have at least 3 levels. So for a factor. So that means if you have, for example, 2 by 2 ANOVA or 2 by 2 by 2 repeated measures ANOVA, so you don't have to worry about sphericity. Only if you have at least one factor that has more than 2 levels, you have to worry about the sphericity assumption. And so what is meant by so this sphericity assumption? So it basically means that if you take each pair of conditions, right? So if you have in the cake example, we have chocolate, lemon, and I don't forget the third one, let's say it's strawberry cake. Then you take, right, so the difference between scores between chocolate and lemon, chocolate and strawberry, and lemon and strawberry. Right? So you calculate the differences between the scores for the all possible pairs of conditions. And then you check whether these differences have the same variance. And that is what sphericity means, right? So that's the variances for all combinations. So for the different scores for all combinations of conditions are equal. If sphericity is violated, so it's a big problem because then our test statistic does no longer follow the F distribution. You have an increased type 1 error rate. And so that's a problem, right? So one way to deal with that is to adjust the degrees of freedom to correct for this bias. So basically, you're just reducing the degrees of freedom, right, to make the F statistic more conservative. We'll talk about that in a minute. Just want to illustrate first what this sphericity assumption means, right? So let's assume we have 5 subjects. They're shown here, right? These 5 dots are the 5 subjects, and they all participated in 4 different treatment types, A, B, C, and D. Then, so we're calculating the differences, right, between treatment A and B. So for all of the 5 participants, right, we are calculating differences between A and C for all 5 participants, between A and D, B and C, B and D, and C and D. And then the variability of these differences, right, they should be the same. So that means how, right, so only the variability, not the means. The variability should be the same. And we see here that this is roughly the case, right? So so there's not like a huge difference here, so we can assume that this is the case. All right. I just wanted to mention that because it's important. So if you delve deeper into mixed models and the implementation in R, so sphericity is basically a special case, a less restrictive case of compound symmetry, the condition that's called compound symmetry. And so this compound symmetry assumption requires that the different conditions have, so basically it's more, as I said, it's more difficult to accomplish, just in some sense. So compound symmetry requires that all the different conditions or measurement time points have the same standard deviations, and that each pair of conditions has the same correlation, right? So that is what compound symmetry requires. And so it is a sufficient condition for the univariate F test for repeated measures to be valid. So that means if you have compound symmetry, then, right, then so the F test will be valid. And if compound symmetry is given, then sphericity is also given. Yeah? So that one, because it's a more restrictive condition, it implies it. And here is just an illustration of what compound symmetry means, right? So this would be so the case where we have 4 levels or 4 conditions, again for like a one-way repeated measures ANOVA. So these are just the, so this is obviously the so the correlation between so the factor levels themselves, which has to have to be 1, right? And so these are the correlations for between, right? So this, if that is 1, so right, 1, 2, 3, 4, that would be 1 with 2, 1 with 3, 1 with 4, etc., right? 2 with 3, 2 with 4. So in here, so what is required is that these are all identical. Right? So correlations are all identical for all possible pairs. So basically the least restrictive assumption for this variance covariance structure in a design where you have correlated, so non-independent measures, is called the unstructured covariance. And so the unstructured covariance doesn't make any assumptions. So here, not only, so basically, so that means that the variances themselves, right? So, right, so this is the same as I said. So the compound symmetry requires that the variance for all conditions is identical, right? So you multiply that by 1, so you have so the sigma squared here in all these fields, right? So for unstructured covariance, you can have different variances, different standard deviations for each of the conditions, and the correlations can be completely different, right? So you can have unique correlations between condition 1 and 2, condition 1 and 3, etc., etc. So there are no constraints; just have to be finite numbers. So I added a little bit more text actually to that slide, a little bit more advanced. So just for your information, we'll update the slides later, or we'll upload the updated slides later today. But it's just an illustration what the differences are between these conditions. So how do we test for sphericity? There's a test that's called the Mortley's test, and that tests the null hypothesis that variances of the differences between conditions are equal. Yeah, so, and if you have a significant result, that would suggest that the sphericity is violated. If our data are perfectly spherical, then sphericity is 1, otherwise it is less than 1, right? So that is a rule. And our statistical software packages provide estimates of the sphericity. They're called epsilon, right? So epsilon is for sphericity, and then estimates are, so they're different estimates. Okay, so what to do if we have a violation here? So the first one that I mentioned earlier is to adjust the degrees of freedom. So and we do that by multiplying our degrees of freedom by the sphericity estimate that our software provides us with. And there are two common estimators. The first one is called the Greenhouse-Geiser estimate, and the second one is the Hohenfeld estimate. And so, as I said, so you multiply your degrees of freedom by these estimates to correct for the effect of sphericity. And so that makes your F-test more conservative. So there are like certain rules of the thumb. So it's important to keep in mind that the Greenhouse-Geiser estimate is more conservative. And it's probably too conservative when your epsilon is close to 1. So that means when you have a minor violation of the sphericity assumption. And so a general rule is if your epsilon is larger than 0.75, use Hohenfeld. So on the other hand, Hohenfeld has been criticized. So the Hohenfeld estimate has been criticized that it's too liberal, when actually sphericity is very low. So when it's when you have a larger deviation, and so that means so if sorry, that should be smaller than 0.75 here. So that means if your epsilon is smaller than 0.75, you should rather use a Greenhouse-Geiser estimate, right? So that's just rule of thumb. Okay. So a second option is that so if your sphericity assumption is violated, then rather than using repeated measures ANOVA, you can run a MANOVA. So, and I mentioned at the beginning of this class that a MANOVA is a multivariate analysis of variance, right? So you have multiple dependent variables. And in the MANOVA approach to repeated measures analysis, you just treat your different conditions as separate dependent variables. So that means in our cake example, right? So the ratings for cake 1, for the lemon cake would be 1 dependent variable. The ratings for the chocolate cake would be a second dependent variable. And the ratings for the strawberry cake would be the third dependent variable. The advantage is that so multivariate test statistics do not depend on the F distribution, so you don't have to worry about this sphericity assumption. And if you have a sufficiently large sample size, it's a good option, right? And it comes in many software packages comes automatically with your repeated measures ANOVA, for example, in SPSS. So a third option is to use linear mixed effects models. And that allows you to deal with violations of this RISD assumption, because you can allow the model to select its own set of covariances, or you can tell it to use a certain variance covariance structure. Yeah, and that could be compound symmetry, it could be an autoregressive structure, it could be unstructured, it could be variance components, etc., etc. So R has many options there. So it can also deal with unbalanced designs. That's another benefit of linear mixed effects models, and why we want to use them, why we would want to use them. Right, so instead of using least square solution, it uses maximum likelihood methods, which can deal, which do not make so the assumption that the data have to be spherical. Okay, so yeah, anyway, so if the data are balanced, then both methods are safe. If we specify the same covariance structure, of course, right? So if we specify different covariance structure, then the results will differ. All right. So here is another example for repeated measures ANOVA and how to do it in R. So it's another one that's kind of funny. So it's from I assume one of these TV shows, I don't know it, where some celebrities have to eat like so all sorts of disgusting stuff, like different animals. And then so the dependent variables is how long it takes them to throw up. And so then there were 4 animals: a stick insect, so a kangaroo testicle, fish eyeball, and a veggie grub. And so, yeah, how long it takes them to throw up would be the dependent variable. So, right, we have here 4 levels of our independent variable. And so that would be the data for this example. And you can basically check whether sphericity is given here for this particular example, right? So, and then you just calculate the different scores for each participant, for each combination of your factor levels. So that means testicle minus stick, eye minus stick, veggie minus stick, etc., right? And then you check whether those variances look the same. Of course, you test it with Moseley's test. Right? So here they look already very different, right? So that raises the suspicion that sphericity might be violated here. And if you want to test for sphericity, it's not that easy actually in R, because so your standard method for running an ANOVA, so your LM, for example, does not provide you with such a test. So it is implemented though in a package that is called EASY. And so that package has a function that's called EASY ANOVA. And EASY ANOVA basically gives you an output for repeated measures ANOVA. It also can do between subjects design, so you can use EASY ANOVA for everything in R. So EASY ANOVA provides you with the same output that some commercial software packages do, like SPSS and SAS, etc. So it has a little bit odd syntax, so that you have to get used to. So this weird way of like defining the arguments here. So it's a dot and not brackets, no, never mind. But yeah, so that is just a little bit strange. Otherwise, it's pretty straightforward. And you get, so the output provides you with your general, right? So the typical ANOVA output, right? So you get your intercept and the effect of animal is all your test statistics. And then it also provides you with the Moseley's test for sphericity. Yeah, you see here, so the test statistic. And that is a corresponding p-value, and you can see it's significant. So that means you probably want to look at the epsilons. And so then it also gives you as a correction here, the estimates for the Greenhouse Geyser estimate and the Hoinfeld estimate. So you can see, so the epsilon is 0.53 here is a Greenhouse Geyser, and 0.67 is a Hoinfeld estimate. And so you can see that's a corresponding p-value using the greenhouse Geyser estimate. So that is basically what you are doing is, right? So you're multiplying, so this epsilon, so the degrees of freedom is this epsilon value, right? So you take, so degrees of freedom 3, so you calculate 3 times 0.533, it's 1.59, and 3 times 0.66 for Hohenfeld, right? It's 1.99. So these are your numerator degrees of freedom, right? These are your corrected denominator degrees of freedom. So that's right, 21 originally. And then you multiply with these epsilon estimates. And you can see that greenhouse Geyser is more conservative because the corresponding p-value for these corrected degrees of freedom is higher than for Hohenfeld, actually. So here just above our beloved 0.05 threshold, right? And so it's important that when you report these results, then you have to report the corrected degrees of freedom, right? So you have to basically rather, there are these odd numbers then, right? Rather than reporting the original degrees of freedom. Okay. So it's important to keep in mind, just wanted to mention that, and I'm sorry for, this takes me longer. So when you're doing post hoc tests for repeated measures ANOVA, so then, so violation of sphericity has also implications for your post hoc tests. So because these post hoc tests usually use a pooled error term, but if your data are non-spherical, so then your error terms are different for each comparison. If your design is balanced, then you're sort of on the safe side, you just use Bonferroni correction, because Bonferroni correction is robust in terms of type 1 error control. So you can just use your post hoc test using Bonferroni as the adjustment method and you're good. If your design is unbalanced, don't do it. Use linear mixed effects models to estimate the model, and then run your post hoc test using the GLHT function from the multi-comp package that we were talking about yesterday, right? And Almer, so that is so a function from the package ALIMI4. So that's the mixed effects extension of linear models, right? Okay. Yeah, so since our example data set is balanced here, we can just use the pairwise t-test functions that we talked about yesterday, right? Comes as a base package, and then use the Bonferroni method for adjustment, and that should be good. And here's the corresponding output. So and then we can see that so the only significant differences are between kangaroo testicle and stick insect, and stick insect and fish eye, right? So the other ones are not significant. Okay. So then very quickly, I wanted to go over the mixed effects model approach to one-way ANOVA. Sorry, if you give me another 5 minutes, I try to make it fast. Sorry that it's rushed because it's kind of important and not that trivial. So I will try to make it clear. So far, so we have assumed that our parameters that we estimate in our models are unknown constants, right? So in our regression model, we assume that our beta weights, our regression weights are some unknown constant regression coefficients, and that in ANOVA that our group means are some unknown constants as well. And these are referred to as fixed effects, right? So there's one value in the population, one true parameter in the population. So unlike fixed effects, random effects are not unknown constants. Random effects are random variables in populations. That means they can take on different values. And so if you have model that try to estimate both fixed and random effects, we call them mixed effects models, right? So that's where the name comes from. So we have fixed and random effects. And so these models are important for repeated, so basically as an alternative for repeated measures ANOVA, because you can model correlated data. Yeah, so if you include random effects in the model, so random effects basically care of this relatedness of your data. Yeah, so they take care of the correlation structure. You basically explicitly model the correlation structure of your data by including this random effect. And typically this is done by, the simplest way is, so this is done is to include a random intercept for your subject, for a subject factor. And that is basically taking into account that your subjects are a random sample from the population, and that each subject has their idiosyncratic intercept, so the idiosyncratic mean. So that is so something that, as I mentioned earlier, so how much a person likes cake in general, right? So how high an individual person's blood pressure is in general, not only for different times of the day. So you model. So basically this variance component is due to the random selection of subjects from the population, and you take into account that so these subjects have their own basically baseline a value on the or a measure on the dependent variable. Okay, yeah, so that is basically, so we have in this Bush-Tucker example, so that would be if we include a random intercept for each subject, so that means that we take the model estimates the throw up threshold for each individual subject. So right, so how sturdy basically a person's stomach is in general. No matter, I mean, what we are interested in, actually, we're interested in the effect of the animal, right? So what's the different animal, so how the type of animal influences how fast they throw up, but there are also differences in how easily, in general, right? So how sturdy the stomach is, and that, so if you include this random intercept for subject, so this is taken care of. The model is estimating that, right? So and that is why what the beauty of it is that it's basically, so that gets essentially rid of, by doing that, by including that, you're getting rid of the dependence in your data, right? So that eliminates this problem. Yeah, so this is accounted for by your random intercept, by your random factor. So, and what we are doing is, so we are decomposing our variability in our dependent variable in a random subject effect, right, in a fixed condition effect. Right, so we're taking this random between subjects variability out of our effects, out of our variability of our dependent variable, and so separately estimates a fixed condition effect. And the huge advantage is that so we can basically specify what's a correlation structure, so what the dependence of the data looks like. Right, so we don't have to cling to the sphericity assumption that the repeated ANOVA measure model relies on, right? And so otherwise, if the data are not spherical, we're sort of screwed. So we basically can just model that, or have the model estimated for us. Okay. So if you want to express the examples of this Bush-Tucker example as a regression model. So here, right, so it's y is our outcome variable, and then we have so the different dummy variables for the different kinds of animals, right? So stick insect, this is kangaroo testicle, this is fish eye. Then for the last one, we don't need it, right? Just 0. And then we have an additional set of dummy predictors or dummy variables that just code for the individual subjects, right? So they're here denoted by z, right? So and have a different regression coefficient. So this is basically, so Z1 is 1 if it's subject 1, otherwise 0. Z2 codes for subject 2, so it's 2 if it's subject, it's 1 if subject 2, otherwise 0, etc., etc. And then the 8th subject would again be 0, 0, so that we don't need to include a dummy code for that, a dummy variable for that. And so then a shorthand way for this above model to express this model is just to write that's alpha plus so the beta j. So these are the betas for your fixed, basically these are your fixed effects. So that's a condition if, so it's a different animals, right? That's the animal effect here. And your gamma I, so that is, this is the effect, it's a random effect of your subjects. And then you still have this random error term, right? So, and as I mentioned earlier, the gamma y, the gamma I allow each subject to have their own unique regression intercept. That means to have their own mean throw-up times. That is what the random intercept means, and that's what we are specifically estimating in this model. So and in R, we use the function Almer. So Alamer, I don't know, everybody is pronouncing that in different ways. So from the LME4 package. So there are different options though, and Alamer is great, but it sometimes doesn't work for all purposes because it's a little limited in terms of specifying the covariance structure. Right, and that's what the syntax looks like. So you have this so basically almost like a regular model, right? So this is our dependent variables. This is our fixed. So the fixed effect looks exactly like in our regular ANOVA. And then this, in order to code for this random effect, looks a little bit weird at first. So basically, what the way you read that is, so the 1 stands for intercept, and you're just telling R that basically, so it's a factor animal is measured repeatedly across participants, and that basically tell R to estimate so this individual intercept for each participant. Right? Okay. And then in order to test whether animal has an overall effect, which you want to find out, right? So that is what you wanna do when running an ANOVA. You're using this model comparison logic that we have used before, right? So you just come up with a reduced model or a null model, and this null model just excludes all the effects that you want to test. In this case, we want to test what is the effect of animal, and so then we are just defining a null model that does not have the animal effect, and instead we are just so this is an intercept, so-called intercept model. So this model simply has an intercept, right? So it has no basically no predictors that code for animal. So and that is basically animal is replaced by 1. And then we just maintain this random term here, so random subject intercept. And we compare, so using the ANOVA function, we compare this null model with our model from before, right? Where we had specified animal. And that is testing whether basically our animal factor is significant, right? And then, so you have the same output that you're already familiar with, right? So you see that there's a difference in 3 in terms of parameters. That's something to do, how, right? Because you need 3 dummy variables or 3 variables to code for the 4 levels of your animal factor, right? So that's why the difference in parameters is 3 between the null model and the model that includes animal. And you are comparing whether that model does a better job in explaining the variability in the dependent variable. And then you have the different criteria, right? So you have the archaic information criterion. Just a reminder, it's better when it's lower. You have the base information criterion. Also, it's better when it's lower. It has a higher, you can see the difference here is smaller because the base penalizes the number of parameters more, right? So means the more complex model is penalized. So that's why, right? But it's still better. Then you have the log likelihood ratio here, so which is your actual test statistic. And this, it follows a chi-squared distribution, right? With these degrees of freedom, and that is your corresponding p-value. So that shows you that animal is significant. Okay, so if you use the random intercept model, you may say, well, so what about sphericity then? So we know that sphericity assumption is violated. So we don't have the data are not spherical. So what is LME Alamer doing here? So and the that is actually supposed to say Alamer, not LME. LME is from a different function from a different package. So I'll have to correct that. It's important. So the default covariance structure for Alamer is unstructured. Yeah, so that's what we just discussed as unstructured. So that is the only constraint is that so the variance covariance random effect is positive definite. Yeah, so no other assumptions are made. The drawback is that so that often results if you have a relatively small sample, and that's a case for example, for this Bush-Tucker data set here. If you have a relative small sample with few subjects only, then so R cannot estimate the model, because you simply have too many parameters, so you don't have enough degrees of freedom. So that means you have a singular solution, which is not good. That happens at times if you assume an unstructured covariance so basically a correlation or variance covariance matrix. So a workaround is that you can just use or specify a different structure. I mean, we know compound symmetry is violated here, but you can use different options. And so the actually the NLME package has a function LME, and that allows you to use different covariance structures, and you can just basically fit your model using different structures, and then compare the model fit using AIC or BIC, right, to see what is the best structure for your model, what is most appropriate. You can also use the MC-GLMM package, which is basically a multivariate generalized linear model. So that use Markov chain Monte Carlo techniques, and so that is mostly to fit Bayesian. So if you use a Bayesian approach, right? So, but that also gives you like more options. And then there are special purpose packages that also give you more flexibility. So that's all relatively advanced stuff here. That is, if you ever wonder later, right, or get into more advanced analysis, what's going on. So then it can sometimes be tedious to find the information on the internet on your own. That's why I wanted to give you like at least some orientation here, right? If you need that for your master thesis, for example. Okay, so I won't go over choosing contrast because it's exactly the same as for our regular ANOVA between subjects ANOVA. I just wanted to mention for post hoc tests, if you use a mixed linear mixed effects model approach, so you can use either the M-means function from the M-means package, you can use the diff-LS means, or you can use GLHT from the MALFCOM package that we already talked about yesterday. Right, I have here an example for using so the M-means function. So right, so this is just the syntax that tells so the function that you want to do the single comparisons for animal, and here you tell R that you want to test all pairs, right? So of the factor level combinations here. And in this case, it's only one factor, so it's just testing all possible conditions against each other. Right. So you can also use, as I said earlier, you can use GLHT, the GLHT function, which is in many cases probably best compromise. Although the M-means is also great. So no, actually I use it quite a lot. So it's just, if you're familiar with the syntax here already, so then you may want to use that. I'm not getting too confused. So here, right, so that in order to adjust for multiple comparisons, right, so this the syntax, so you have this extra function, linf function, so that is basically that you just pass to GLHT as an extra argument. Okay. Alrighty, so this is not that important. That is, if you have an ANOVA that has a repeated measure factor and between subjects factor, it's not that much news, right? It's just as a way so your test variance is a little bit different than in the other two models, but it's not a big deal. So conceptually, it's all the same. I'll leave that in here, but I don't want to use any more of your time than I have already. I hope that made sense, sort of, despite being a little bit rushed. And if you have questions about that, how to implement the repeated measures in ANOVA and R using the mixed effects models, let me know. It is important. it is important, and it's definitely in many ways a better idea than doing it in SPSS and using the standard ANOVA approach, and understanding how mixed models work is important. They're very popular, and more reviewers and editors are asking for it. So because they are so much better handling all sorts of issues that you could have with your data, like missing data, right? So unbalanced designs, etc., etc. So that is why I would encourage you to get familiar with the concept. So again, so you can, I said that multiple times over the semester, you can give an entire class on linear mixed models only. So we were just barely scratching the surface here, but I hope that it will give you some basic idea, right? So it's just one more thing that I wanted to mention. So here we have only talked about the most about the symbols of all implementations. So the random, basically including a random intercept. So you can also include a random slope, which would mean that, so basically, so not only allowing a different mean effect for each subject, you would allow that actually the condition effect is different for each subject. So that right, if you again take our blood pressure example, that for example, some participants have a steeper slope and some participants have a flatter slope, so that you wouldn't treat that as an error variance, but you would basically explicitly model that, right, as a random effect. So that's called the random slopes. And then there are all sorts of highly complex designs where factors at different levels are nested within each other. So that, and that is all this, basically there's a whole universe, right? So of the mixed effects models that we, of course, we can cover here, but at least I wanted to mention it. All right, so then thanks for staying with me, and sorry for not leaving you any time, despite what I had promised.
It's okay. I wanted to mention something real quick. For assignment 9, the honeymoon period data is not on Blackboard.
Oh.
Or at least I couldn't find it.
It's not like, on Blackboard. Okay.
Like it should be on the data folder, and I didn't see it there.
I will upload that right away. I apologize for that.
It's okay. Thank you. I just wanted to catch you at the end to tell you, but thank you.
Okay, super. Anything else?
No, that's, I'm sorry.
All right.
Anybody else?
All righty. So then, yeah.
Dr. Unger?
Yeah.
I just had one small curiosity. I don't think this is the case, and it's probably me just reading too deeply into the data set, but are we supposed to make the, I forgot what it's called, the BMI data sets into a long data set rather than wide, or is that not necessary at all?
That might be required, yeah.
Okay.
That might be right. If you have specific question about that, it might be good to post that or to send me an email directly, and then what, okay, wait a second, just open the let me quickly open this. Where is it? Can't find it. Okay. Yep. Yeah, that has to be long format. I mean, it always depends on what specific method you're using. So what, but most functions requires a long format. Yeah, and then if in case I haven't mentioned that, so you can use a the pivot longer, pivot wider, right? So that is the more modern version of, so you can also use a reshape package, so reshape or shape2 package as a functions in the reshape package, but the pivot longer, pivot wider is much more intuitive and superior, in my opinion. So, and R encourages so to use that instead. So to very quickly reshape your data.
Okay, makes sense.
Now, if you have questions about that, then let me know. But if you can just type it into R, so pivot longer, pivot wider, so it's, and then it will come up. So it's it's in the base package, right? So it doesn't, it's not like a, no, it's not true. It's tidier. It's a tidier package. It's not a base package. It's tidier. So it's basically it's pivot. So it's pivot underscore longer and pivot underscore wider, and it's tidier. So it's TIDYR package, and that is really great. These functions are great. All right. Any other questions? Concerns? Yeah. Right. So if you need more time with the as a last assignment, I mean it's also I don't want to encourage you to take more, basically to stretch that out, because then it might interfere with the final preparation. So then let me know. It would be okay. Yeah. But so please get started on it, because I think it requires a little bit more. Might require more time than the previous assignments. All right. Anything else, or? Okay, then enjoy the rest of your evening, and I'll see you all next week. Last time this semester, and we're talking about Bayesian statistics. Very exciting. I'm excited. I'll see you then.
I look forward to that too, actually.
Huh?
I'm also looking forward to that.
Okay. All righty. Good night.